graph here. This yellow one, it shows us the radiation coming from the sun, right, before it reaches the atmosphere of Earth. Okay, so when you go out of Earth atmosphere, if you try to measure the emission intensity of sun versus wavelength, this is what you get. So as you can see, the sun contains visible spectrum 400 to 700. Besides, it also contains a lot of ultraviolet and a lot of infrared. Okay, so that's a complete spectrum of the sun. However, when the sun reaches the Earth, it must pass through the Earth atmosphere. And the Earth atmosphere has water, has oxygen, and many other gases. So all these absorb part of the sun spectrum. So when the spectrum reaches the Earth, what you really detect will be the red one. You see some parts are missing because these have been absorbed by a gas molecule. Okay? So to some extent, we are protected by the Earth atmosphere because you see part of the ultraviolet has been filtered out by the Earth atmosphere. But there's still some. Is it clear? Okay, so this is what the sun radiation looks like. Now, then the question says that you're asked to assume that the sun behaves like a black body. Is that really the case? Now, we take the black body radiation at 5778 Kelvin. Can you see this line here? Can you see this line? This line is the Planck's radiation law at this temperature. Can you see that it almost overlaps with the emission from the sun before it reaches the atmosphere? It's not perfect, but it's quite close. Therefore, it's valid to say that the sun behaves like a black body and the temperature is 5778 Kelvin. So from there, you more or less can estimate the sun's temperature is around that type of temperature. 5000 plus to 6000 Kelvin. Is it clear? Okay, so coming back to this problem, okay, what you are asked to do is that you are given the power emitted from the sun, you are given the surface area, and you are asked to estimate the temperature of the sun. Okay, in fact, from what I'm showing you, you already know the value is around there. But based on the numbers even in this question, we'll get something very close, but not exactly this one. Okay. So first of all, I want to introduce Stevens-Boltzmann's law. Stevens-Boltzmann's law gives us the total output power from any object as a function of temperature. And this is a universal equation to describe any object. Now what we can immediately notice is that the total output power, now when I say total, it means across all wavelength. From wavelength equal to 0 to infinity, all spectrum. The total output power is a function of T to the power 4. What does it mean? It means that when you heat up an object, the total intensity you can collect from this object increases very fast with temperature at the rate of T to the power 4. Okay? And this sigma here is called the Stevens-Boltzmann's constant. It's a universal constant. And this epsilon here is called the emissivity. Emissivity can range from 0 to 1. It measures how good an object emits. For black body, which is the best emitter, emissivity is 1. For things that are not black body, the emissivity will be less than 1. Okay? Now, then how is this related to Planck's radiation law? Remember the Planck's radiation law, the area under the curve gives me the power emitted per unit area. If I want to find the total output power, that means across all wavelengths, I need to do this. I integrate the Planck's radiation law from 0 to infinity wavelength. Now, just now I told you that this R function, when you integrate from any lambda 1 to lambda 2, there is no closed form. But when you integrate across the whole spectrum, there is closed form. If you're interested, you can find some advanced textbook. They'll show you how to perform the integral. But it involves some special function. Okay, when we integrate Planck's radiation law from 0 to infinity, in fact, it will give us the total output power. And you can show that that integral is equal sigma T to the power 4, which is exactly what Stevens-Boltzmann law is trying to tell us. Because remember, for black body, the emissivity is 1. So, by showing you this, I want you to differentiate what is the difference between Stevens-Boltzmann's law and the Planck's radiation law. When you consider Planck radiation law across all wavelengths, it becomes the total, which is Stevens-Boltzmann's law. But like in the previous question, when we are only interested from 500 to 501, can you apply Stevens-Boltzmann's law? In the previous question, when we are interested in emission from 500 to 501 only, isn't it? Can you apply Stevens-Boltzmann's law? Answer is no, because Stevens-Boltzmann's law gives us across all wavelength. But question 2 is only interested in photon from 500 to 501. It's a different type of problem. Are you all clear about this now? Okay? So I apply Stevens-Boltzmann's law because I know the total output power from the sun. I know emissivity is 1. I know sigma, Stevens-Boltzmann constant. Therefore, I can find the temperature. The temperature of the sun is 5.75 times 10 to the power 3. Now, of course, this intensity we can solve because we are given the power and the surface area of the sun. So you know how much power is coming out per unit area from the sun. So from there we solve. You see, it's 5.75, very close to this. In fact, if you draw 5.75, means 5,750 Kelvin, you also obtain a black body radiation that's quite close to the other side. In fact, if you just vary by several Kelvin, the black body radiation will shift, but you can't see with your eyes. Is it clear? And this one I took it from one of the websites. They estimated it to be 5778. Our calculation shows it's about 5750. Any question? I didn't see any expression again. I'm not sure whether you all follow me, you understand it? At least you should now know how you apply Planck's radiation law to calculate over a band of wavelength, and then what is this Stevens-Boltzmann's law. Okay, can. Okay, there are other things.